Today we are diving into GenSim, a powerful Python library that enables semantic understanding of text data at scale, while modern language models like ChatGPT-4 grab headlines. GenSim remains a cornerstone for efficient, interpretable, and scalable natural language processing. Whether you are a data scientist, developer, or a business analyst, understanding GenSim will empower you to extract meaningful insight from unstructured data without needing massive computational forces. Consider this: if you are building a search engine for academic papers, and a traditional keyword-based approach might fail to recognize that deep learning or neural network often remains two similar concepts. GenSim solves this by capturing semantic relationship between words, enabling smarter research, recommendation systems, and document clustering. Scope and motivation. Why should you care about GenSim? Because text data is growing exponentially every minute. 500 hours of YouTube videos with captions, 500k of tweets, and millions of product reviews are generated every hour. Traditional tools like regex or basic keywords such as struggle with the three key challenges: ambiguity. Words like apple, like it might be a company, it might be a fruit. Words like python, it might be a language and it might be a snake. It requires context aware analysis. Scale. Processing terabytes of text effectively demands optimized algorithms. Semantics. Synonyms like car versus automobile and related items like iPhone versus smartphone confuse simple search methods. GenSim addresses these challenges with unsupervised machine learning, making it indispensable. In e-commerce, analyzing customer reviews to detect themes like shipping delays or product quality. In healthcare, clustering patient records to identify common symptoms or treating responses. In legal tech, automatic categorizing case law by topics like intellectual property or employment disputes. What is GenSim? GenSim is an open source Python library for unsupervised NLP and topic modeling created in 2008 by Radim Redek. Unlike other information retrieval tools, GenSim is designed for efficiency and scalability. It can process Wikipedia-sized datasets on a single machine without crashing your RAM. Key features are memory efficiency. It uses streaming data processing, no need to load everything into RAM. Algorithm powerhouse. It implements TF IDF for keyword weighting and LSA LSI for topic modeling, and word to vector and doc to vector for semantic search. And simple APIs let you train word to vector model in 5 lines of code. Like, if you consider analytic as a Swiss Army knife, and GenSim we can consider it as a power drill, which is specialized, efficient, and industrial strength, which is having industrial strength. And the name GenSim came from generate similarity, reflecting its core strength in semantic analysis. TF-IDF, term frequency inverse document frequency, is the backbone of modern search engines. Here is how it works. Term frequency measures how often a term appears in the document, and inverse document frequency penalizes common terms like the, a, or that appear in the too many documents. And topic model with LSI. Latent semantic indexing uncovers hidden themes in large text collections using singular value decomposition, thinking of its compressing a 10,000 dimensional word space into 100 interpretable topics. How it works. Decompose a term document matrix into topics. Each topic is weighted into a mix of words. Topic 1 equals to some 0.6 into election plus 0.4 into vote. In real world applications, news aggregation, cluster articles into politics, tech, and sports. In academic research, it considers as automatically categorize papers by field. In customer feedback, detect recurrent themes like pricing, compliance, or feature request. Example, a media company uses LSI to tag 50,000 news articles and reducing manual labeling effort by 70%. Semantic search with word to vector. Word to vector is a GenSim star feature. It learns vector representation of words, capturing semantic relationship like king minus man plus woman equals to king and iPhone equals to smartphone. How GemSim implements it. Skipgram predicts context word given by a target word. SIBO predicts a target word from context words. Negative sampling effectively trains on large corpora. Real world uses like in healthcare, similar product recommendations. In customer support, match forgot password to relevant FAQs. In healthcare, to find semantically related medical terms in patient notes. Example, an online retail boosts sales by 15% using word to vector to recommend visually dissimilar but semantically related products like yoga mat and meditation app.
Coming to the performance optimizations, we have challenges, optimization techniques, and the practices. So, in the challenges we faced is like the large text data sets can be overwhelming memories and CPU resources. In inefficiency in vectorization and querying, and in optimization techniques, we have four of them, which is streaming API, parallel processing, memory mapping, and incremental data updates. So in streaming API, we have processing data in batches into minimize memory usages. Parallel processing, we use like utilization of memory codes for model training. And memory mapping, we have load models and efficiency with NumPy array. And in incremental data sets, we update models iteratively without retraining. The practice we used the gemsins gemsins for a large scale data sets and optimization of the size by filtering low frequency words. Coming to the next slide, real world case studies. So in real world case studies, we'll be overviewing the application of gemsins in document by classification of project for for a text. So in the objective, will improve the search and retrieval for the text. In the approach, we'll be using pre-processed text data with gemsins, which is applied by TF, IFT, and LS to recreate the semantic search system. Used word to vector to identify relative terms for enhanced query expansion. In the result, we found out that 30% increase in search accuracy and reduced in response by 40%. So, and in the limitations, we have the memory usage, accuracy challenges, and training time. So, in memory usage, we have large modules can consume significant memory, and accuracy challenges our models may underperform for a high complex semantic task. And the training time modules on the large datasets can be slow. And the workabouts and the solutions we did on this is like using of partial fitting by iterating updating models combined of Jensen's with the most powerful modules like transformers based modules and utilization of optimization of matrix factorization techniques to speed up the SUD by pairing up with the Cuba enhanced libraries and getting started with the installation here. The basic workflows are the data preparation, which is pre-processing and cleaning the text. And next goes to the vectorization, converting the text into packs of words. And next is like the model training of application of algorithms such as LSI and word to vector. And the fourth is search and evaluation, which is like query co-ops and evaluating the performance. So
In this code, we demonstrate how to use GenSim for information retrieval on a collection of cricket-related documents. The process begins by pre-processing and tokenizing the text. The simple pre-process function is applied to each document to break it down into a list of lowercase words. removing punctuation and other non-essential characters. After tokenization, we create a dictionary using Gensim's Corpora dictionary, which assigns a unique integer ID to each unique word across all documents. Next, we convert the documents into a bag of words format using the dictionary. The bag of words representation is a list of tuples, each containing a word ID and its frequency in the document. This representation is then used to generate a TF-IDF. Uh, TF-IDF adjusts the importance of words by downweighing the that appear frequently across many documents and emphasizing those that are unique to the specific document. With the TF-IDF model applied, we create a similarity index using similarities.matrix similarity, which allows us to compare the query to document effectively. When a query like who is MS Dhoni is provided, it is processed in the same way as document tokenized, converting it to BOW and transformed into TF-IDF representation. The similarity between the query and each document is calculated, and the results are sorted by relevance. Finally, the ranked documents along with the similarity scores are displayed, with the most relevant documents appearing at the top based and highest similarity to the query. Now I will run the code, and this will be the results, which is having 0.1536 is the top one. MS Dhoni is known for incredible finishing skills, and he is the question. This is the question.
Going to the next slide, the future of Jensen's and LLMS. So in this, we will be doing the emerging trends. So interrogation of Jensen's with the large language modules like GPT, combining traditional NPL pipelines with transforming based modules. And the challenges we face is scaling module to handle larger and multilinguistic text, improving schematic understanding beyond keyboard based approaches, and the future potential use of hybrid modules that combine TF, IDF, and training embedded, enhanced context search powered by Jamson's efficiency modules, automating the query expansion and relating the scores with the deep learning. And coming to the conclusion, Jensen provide a robust framework for bridging the gap between the keyboard-based and the schematic search, ideal for mid-scale and NLP's pipelines. From this, the key advantages is memory efficiency with streaming capabilities, extensibility, and easy to interrogate with other Python NLP tools. The future outlooks are enhanced performance with the hybrid modules, more like seamless integration with the large language modules for the complex NLP tasks. Thank you.